Hey there, physics students. Welcome back to another edition of Rapid Review for Honors Physics. Today our topic is simple harmonic motion, and there's so much to say. I got to get right into it. Let me start by showing you a demonstration of a spring and a mass, a system that I've created of a spring and a mass. You'll recognize already, because you've studied spring behavior in a static sense, that this static situation has a mass, force of gravity pulling down on it, and a spring pulling back, and it's in equilibrium right now. So the spring force has to do with how much I have stretched it, as you've learned already, right? So you know that the force has to do with how much I have stretched the spring. What we're going to consider today is this system here, where the spring is now going to allow me to bounce this thing back up and down, and it will bounce up and down around its new equilibrium position, right? So with no mass, there would be a different equilibrium position, right? But here I have an equilibrium position for this system that is right here. I've noted it with the paint tape. Let's get this thing going, and then we can start to analyze it. That right now, moving around, is a pattern we call simple harmonic motion. It will move if we look at the position of that thing. I'm going to use Y because it's vertical. If we look at the position of that thing around the equilibrium position, and we studied it, we would see it's essentially a sine x versus x kind of function. This is as a function of time. Okay? Now, there's a lot of vocabulary to study in this topic. I will trust you've seen these before, and I will encourage you to freeze the video and read all of this if you haven't been exposed to it yet. But I'll try to use these words in context as we go rather than read the definitions. So at this point, we're looking at an oscillating system with a frequency f, right? That's in cycles per second, and that is the reciprocal of its period t, represented by uppercase. I'll remind you that my lowercase f looks a little bit funny to the uninitiated, but you know now what I mean. Okay? So period in seconds, frequency in cycles per second, also known as hertz. They mean the same thing. Okay? More vocabulary. Simple harmonic motion means the thing is moving up and down in a regular pattern, and it's moving around an equilibrium position where there is a restoring force trying to pull it back to the equilibrium position. Let's take a look at this a little more closely in this picture. I'm showing you 4 different instances in time. These are sequential, and if you look at the system in position number 1, it's in equilibrium. There's no unbalanced force. But in position 2, there is a restoring force. There's an unbalanced force because the force of gravity is more, the magnitude of the force of gravity is more than the magnitude of the force of the spring. Here's all 4 cases right now shown in their force diagrams, and you will see what I mean. F sub g is a constant, of course, because we're here on the surface of the Earth. We can't change that. But the spring force varies along the way, along the path. I encourage you to study this and look at position as a function of time, and velocity as a function of time, and even, this is tricky, acceleration as a function of time. Because if you study it and you look at the unbalanced forces, you will see that the acceleration, anytime the thing is above the equilibrium position, the acceleration is negative, and anytime the mass is below the equilibrium position, the acceleration is positive. I leave that as an exercise for you to study. Convince yourself. If you convince yourself and believe it and understand it, you're doing very well. More vocabulary. We've defined amplitude by now as the distance, how extremely it moves up and down, and that's in units of meters or some length unit, and it's measured importantly from the equilibrium position. Common mistake, don't look at peak to peak amplitude. It's not there. It's what's shown here in the picture. We will see if we look at the bouncing spring again soon. Let's check up on that. Can we just switch the camera to that thing? Is it bouncing? Yeah, it looks like it's bouncing. Good. We're going to come back to that again. The fact that that gradually loses amplitude is called damping. And the more, this gets into energy, but the more energy that's lost when it goes up and down, the faster it loses energy, we would say the spring has more damping. The spring I'm using right now is pretty remarkable. It has very little damping in it. It's made out of a special steel called, if I'm not mistaken, spring steel. Let's go back to vocabulary. That thing is bouncing up and down at a natural frequency. If I grabbed the top of that spring and tried to shake it all around up and down in any way I wanted to, the spring and mass system would insist on vibrating at its natural frequency. I can't mess with that. It just wants to move at that frequency. I could also say that period, right? In fact, I can calculate the period. If I know the spring constant K, I'll remind you that K is the K that you see in the spring equation, right? F equals Kx, or in vector form, F equals Kx with the arrows. You need the minus sign if you're going to do it in vector form. That's the spring constant. If you know the spring constant and you know the mass, you can predict the period. This works remarkably well. We've done this in class. We've done different labs with different unknowns, and you can always solve for the unknown if you know the other bits in there. So you can solve for T, you can solve for K, you can solve for M if you want to. The pendulum is very similar, and I'm going to just jump right to the punchline here. The period of oscillation for a pendulum, it looks a lot like the equation for the period of oscillation for a mass plus spring system. And that is because it moves in simple harmonic motion. So it's pretty much similar math, the same math that drives the result. There's a restoring force, and the thing tries to move back to its equilibrium position, but there's inertia carrying it through, just like there is with the mass plus spring system. One of the surprising things about the period of oscillation for a pendulum is that it's independent of mass. Might not be intuitively obvious that that should be. Oh, you're going to practice all this vocabulary we have used, but I will say one student has asked me once, what's so simple about simple harmonic motion? I thought it was a good question. The reference is that this oscillation happens in the form of one sine wave, right? So you could imagine a system that is more complicated that would do multiple sine waves at the same time, added together through superposition, and so on. So that is something you could study in a future physics class. And there's a whole set of analysis mathematically called a Fourier series. You can look that up, F-O-U-R-I-E-R. Fourier series talks about how you can separate a system out into various sine wave components so that if you add them all together, you get the right answer, but each little slice of it is a simple harmonic motion. Let's move right along. I wanted to discuss the idea of analyzing equations that you see. These questions are really good ones, and if you haven't seen this in class, I recommend that you practice some of these. The basic question is, if I do something to, I'll pick one here, if I do something to T, what happens to F? And you can see that if T gets bigger, F gets smaller, right? By the same amount. It's a little trickier if you look at square roots, right? So here, if I want to double T to get 2x, 2 times T, I have to quadruple L. I have to get L times 4 because it's under the square root. Take a look at some of those questions, practice some of those answers, and I encourage you when you see new equations to approach them with that kind of a Curiosity. What happens if I do this to one variable? How will it affect something else? It gets trickier, right, when you have square roots and you have things in denominators. It takes a little practice. But it's a really useful skill. I encourage you to practice that, maybe with a study partner. I point out here just the similar form of the two equations for a pendulum and a mass on a spring. I find that interesting. I also find this toy pretty interesting. I wish they made them for adults, but they don't. And for the curious, it's called a jolly jumper. I want a jolly jumper, but I can't get one that I know of. Quick bonus for you is potential energy in a spring. You can calculate that. We once took that equation. We took apart one of the projectile launchers in our class. We measured the spring constant. We determined how much potential energy you could put into a steel ball when you compressed it into a spring launcher, a projectile launcher, and you could calculate what the velocity must be by conserving energy. We did all that. It actually works. It's pretty impressive. So you can mess around with that equation too. You can solve some problems involving potential energy in a spring if you are inspired. Let's take one last look at our mass plus spring system and see what happened. It looks like it lost a little bit of amplitude, so there's some damping in the system. I'm not surprised. That will go for quite a while longer, actually, in that it'll just gradually decay in amplitude, and actually the form of that decay follows an exponential decay. That's would be a great topic for another time. Let's stop there. But there we go, mass on spring. That is all I have to say about this topic. I'll see you next time for Rapid Review.